geometric progression. We shall now study the next type of progression known as geometric progression. Consider the sequence 1, 5, 25, 125 and so on. Can we find the next two terms of the sequence? Yes, we can. What are they? Here, each term is obtained by multiplying the previous term by 5. Therefore, the next two terms are 125 into 5, that is 625, and 625 into 5, that is 3125. Let us consider another sequence 4, 8, 16, 32 and so on. What are the next two terms of this sequence? In this sequence, each term is obtained by multiplying the previous term by 2. Therefore, the next two terms of the sequence are 32 into 2, which is 64, and 64 into 2, which is 128. Let us consider one more sequence 3, 3, 3, 3 and so on. What are the next two terms of this sequence? The next two terms of this sequence are the same number 3, since each term is obtained by multiplying the previous term by 1. Are these examples of sequences an AP? The sequences given in example 1 and 2 are not an AP, since the difference between two consecutive terms is not a constant. But the sequence given in example 3 is an AP, since the common difference is 0. There is another common relation between each term of the sequence. What is the common relation between each term of the given sequences? In the first example, the ratio of two consecutive terms is 5. In the second example, the ratio of two consecutive terms is 2. In the third example, the ratio of two consecutive terms is 1. Such a type of sequence is known as geometric progression. Let us now define geometric progression. A geometric progression is a sequence in which the ratio of two consecutive terms is constant. Generally, the common ratio is denoted as R. Or, a geometric progression is a sequence formed by multiplying each term except the first term T1 by a non-zero number R. This number R is called the common ratio. Thus, if a sequence T1, T2, T3 and so on is a GP, then T2 upon T1 is R, T3 upon T2 is R, T4 upon T3 is R, and so on. That is, T2 is T1 into R, T3 is T2 into R, T4 is T3 into R, and so on. Since division by 0 is not defined, neither the common ratio nor any term of a GP can be 0. Consider a GP with all terms positive 5, 10, 20, 40 and so on. What is the ratio between two consecutive terms in this GP? T2 upon T1 is 10 upon 5 is 2. T3 upon T2 is 20 upon 10 is 2. T4 upon T3 is 40 upon 20 is 2, and so on. Now let us consider a GP with all terms negative. -1, -3, -9, -27 and so on. What is the ratio between two consecutive terms in this GP? T2 upon T1 is -3 upon -1 is 3. T3 upon T2 is -9 upon -3 is 3. T4 upon T3 is -27 upon -9 is 3, and so on. In both the examples, the common ratio R is positive. What do you conclude from this? If the common ratio R is a positive number, then all the terms of the GP will have the same sign. In this case, all the terms of the GP will be either positive or negative. Let us consider another GP. 1, minus 4, 16, minus 64, and so on. What is the ratio between two consecutive terms in this GP? Here, T2 upon T1 is minus 4 upon 1, which is minus 4. T3 upon T2 is 16 upon minus 4, which is minus 4. T4 upon T3 is minus 64 upon 16, which is minus 4. What do you understand from this example? If the common ratio R is a negative number, then any two consecutive terms of the GP will have opposite signs. In this case, the GP contains alternatively positive and negative terms. Let us now solve an example based on GP. Here, we have to find the missing terms. What is the common ratio of the progression 4, 40, 4000? The ratio of 40 and 4 is 10. Therefore, the common ratio is 10. What is the third term in this progression? The third term is 40 into 10, that is 400. Now we will consider the progression 3, minus 3, 3 and dash. What is the fourth term of this progression? Since the common ratio is minus 1, the fourth term is 3 into minus 1, that is minus 3. What is the third term and the fifth term in the next progression? Since the common ratio is 1 upon 3, the third term is 3 into 1 upon 3, that is 1. And the fifth term is 1 upon 3 into 1 upon 3, which is equal to 1 upon 9. General representation of a GP. As in AP, in GP2, we will learn the general representation, the nth term, the sum of the first n terms and the particular terms. We will start with the general representation of a GP. Consider the GP 6, 12, 24, 48 and so on. Here A is 6 and R is 2. The first term T1 is 6 is A. The second term T2 is 12. This can be written as 6 into 2, which is A into R. The third term, T3, is 24. This can be written as 6 into 4, that is 6 into 2 square, which is A into R square. The fourth term, T4, is 48. 48 can be written as 6 into 8, that is 6 into 2 cube, which is A into R cube, and so on. Thus, in general, a GP can be expressed as A, AR, AR square, AR cube, and so on, where A is the first term and R is the common ratio. If A and R is given, then we can find any value of GP by substituting the values. Let us solve an example based on what we have learned now. Write down the first 5 terms of the GP, which has first term 1 and common ratio 4. Here A is 1 and r is 4. In general, we can write the first 5 terms of a GP as a, ar, ar square, ar cube and ar raised to 4. Substituting the values of a and r, we get T1 is a is 1. T2 is ar is 1 into 4 is 4. T3 is ar square, which is 1 into 4 square, which is 16. T4 is ar cube, is 1 into 4 cube, is 64. T5 is ar raised to 4, which is 1 into 4 raised to 4, which is 256. Therefore, the first 5 terms of the GP with first term 1 and the common ratio 4 are 1, 4, 16, 64 and 256. The nth term of a GP. We have learned that the nth term of a sequence is the general term of the sequence, and the nth term of an AP is the general term of an AP. In GP2, the nth term is considered as its general term. We will now learn how to write the nth term of a GP. Consider a GP with the first term A and the common ratio R. That is A, AR, AR raised to 2, AR raised to 3 and so on. Here the first term T1 is A. The second term T2 is AR and it can be written as AR raised to 2 minus 1. The third term T3 is AR raised to 2. It can be written as AR raised to 3 minus 1. How will you write the fourth term? The fourth term T4 is AR raised to 3. It can be written as AR raised to 4 minus 1. What will be the nth term of this GP? The nth term Tn is AR raised to n minus 1. Thus the nth term of a GP with the first term A and the common ratio R is Tn is AR raised to n minus 1. We can find any term of a given GP by using this formula. Let us now solve an example by using the formula Tn is AR raised to n minus 1. Find the 15th term of the GP, 3, 12, 48, 192 and so on. The first term A is given as 3 and the common ratio R is 4. We know the formula Tn is AR raised to n minus 1. We can find the value of T15 by substituting n is 15, A is 3 and R is 4. Therefore, T15 is 3 into 4 raised to 15 minus 1, which is equal to 3 into 4 raised to 14. Therefore, the 15th term of the given GP is 3 into 4 raised to 14. Let us now solve some more questions. Find the 4th and the 9th term of a GP whose first term is 4 and the common ratio is 2. Here, the first term A is given as 4 and the common ratio R is given as 2. We know the formula Tn is AR raised to n minus 1. To find the 4th term T4, we have to substitute n is 4, A is 4 and R is 2 in the formula. Therefore, T4 is 4 into 2 raised to 4 minus 1, which on simplification is 32. Therefore, the fourth term of the GP is 32. Substituting n is 9, a is 4 and r is 2 in the formula, we can find T9. Therefore, T9 is 4 into 2 raised to 9 minus 1, which on simplification is 1024. Therefore, the ninth term of the GP is 1024. Let us solve one more problem. Find the 69th term of the GP, 1, minus 1, 1, minus 1 and so on. Here, the first term A is 1 and the common ratio R is minus 1. We know the formula Tn is A R raised to n minus 1. Substituting n is 69, A is 1 and R is minus 1 in the formula, we get T69 is 1 into minus 1 raised to 69 minus 1, which is equal to 1 into minus 1 raised to 68. We know that minus 1 raised to 68 is 1, since the index is an even number. Therefore, T69 is 1. Therefore, the 69th term of the given GP is 1. The sum of the first n terms of a geometric progression. Consider the GP 3, 6, 12, 24 and so on. What is the sum of the first two terms of this GP? The sum of the first two terms, S2, is 3 plus 6, which is 9. What is the sum of the first three terms of this GP? The sum of the first three terms, S3, is 3 plus 6 plus 12, which is 21. What is the sum of the first four terms of this GP? The sum of the first four terms, S4, is 3 plus 6 plus 12 plus 24, which is 45. How can you find the sum of the first n terms of this GP? We can find the sum of the first n terms, Sn, by adding the first n terms. But this method of finding the total is tedious. As in AP, in GP2, there is a formula to find the sum of the first n terms. We will now derive the formula for the sum of the first n terms of a GP. We will consider a GP A, AR, AR raised to 2, AR raised to 3 and so on up till AR raised to n minus 1, where R is not equal to 1. Let the sum of the first n terms of the GP be Sn, which is equal to A plus AR plus AR raised to 2 plus AR raised to 3 and so on up to plus AR raised to n minus 1. Multiplying by R on both sides, we get Rsn is AR plus AR raised to 2 plus AR raised to 3 plus and so on up till plus AR raised to n minus 1 plus AR raised to n. We will now subtract R into Sn from Sn. Cancelling the common terms, we get Sn minus R into Sn is A minus AR raised to n. Taking out the common terms, we get Sn into 1 minus R is A into 1 minus R raised to n. Since R is not equal to 1, 1 minus R is not equal to 0. Therefore, dividing by 1 minus R, we get Sn is a into 1 minus r raised to n upon 1 minus r. We will use this formula when r is less than 1. This can also be written as Sn is a into r raised to n minus 1 upon r minus 1. We will use this formula when r is greater than 1. Thus, we can use this formula to find the sum of the first n terms of a GP. By substituting the values of n, a and r in this formula, we can find the sum of any terms. The above formula is applicable when r is not equal to 1. When the common ratio r is 1, then the GP becomes a, and so on. Therefore, the sum of the first n terms Sn is Na. Let us now solve an example by using the formula for Sn. Find S9 for a GP 2, minus 4, 8, minus 16 and so on. Here A is 2 and R is minus 2. This means R is less than 1. Since R is less than 1, the formula to find Sn is a into 1 minus r raised to n upon 1 minus r. Substituting n is 9, a is 2 and r is minus 2 in this formula, we get S9 is 2 into 1 minus of minus 2 raised to 9 upon 1 minus of minus 2, which on simplification is equal to 342. Therefore, S9 is 342. We will now solve a few more questions by using the formula for Sn. If S3 is 31 and S6 is 3906, then find A and R. We have to find the first term and the common ratio by using S3 and S6. We know the formula Sn is a into r raised to n minus 1 upon r minus 1. Therefore, S3 is a into r raised to 3 minus 1 upon r minus 1. But S3 is given as 31. Therefore, 31 is a into r raised to 3 minus 1 upon r minus 1. We will denote this as equation 1. Substituting n is 6 in the formula, S6 is a into r raised to 6 minus 1 upon r minus 1. But S6 is given as 3906. Therefore, 3906 is a into r raised to 6 minus 1 upon r minus 1. Let us denote this as equation 2. Dividing S6 by S3, we get 3906 upon 31 is a into r raised to 6 minus 1 upon r minus 1 divided by a into r raised to 3 minus 1 upon r minus 1. On simplification and cancelling the common term r raised to 3 minus 1, we get 126 is r raised to 3 plus 1. Therefore, r raised to 3 is 125. Therefore, r is 5. Substituting the value of r is 5 in 31 is a into r raised to 3 minus 1 upon r minus 1, we get 31 is a into 5 raised to 3 minus 1 upon 5 minus 1. On simplifying, we get A is 1. Therefore, A is 1 and R is 5. Particular terms in a GP. As in AP, year 2 we will learn how to select the terms of GP. While solving the problems of GP, it is convenient to select the terms in such a manner that on taking the product of the terms, one unknown is eliminated automatically. For example, if we want to select 3 consecutive terms of a GP, it can be assumed as A upon R, A, AR. Here, when we multiply these 3 terms, R will be eliminated and we can find the value of A. To find 4 consecutive terms, it can be assumed as A upon R raised to 3, A upon R, AR, A R raised to 3, so that on multiplication, R will be eliminated. But note that here the common ratio is R raised to 2. To find 5 consecutive terms, we can assume the terms as A upon R raised to 2, A upon R, A, AR, A, R raised to 2. Here too on multiplication, R will be eliminated. Let us now solve an example by assuming the terms of a GP as explained. Find 3 consecutive terms in a GP such that the sum of the second and third term is 60 and the product of all the 3 is 8,000. Since we want to find the 3 consecutive terms, we will assume the terms as A upon R, A, AR. It is given that the sum of the second and third term is 60. Therefore, A plus AR is 60. It is also given that the product of all the 3 terms is 8,000. Therefore, A upon R into AR is 8,000. Cancelling the common factor R, we get A raised to 3 is 8,000. Therefore, A is 20. Substituting A is 20 in A plus AR is 60, we get 20 plus 20R is 60. On simplifying, we get R is 2. Substituting A is 20 and R is 2 in the assumed terms, we get T1 is 10, T2 is 20 and T3 is 40. Thus, the 3 consecutive terms of the GP are 10, 20, 40. We will now learn arithmetic mean. If 3 numbers A, B, C are in AP, then the middle number B is called the arithmetic mean between the numbers A and C. Let us now find the arithmetic mean between any 2 numbers X and Y. Let the arithmetic mean between the 2 numbers X and Y be A. We know that if A, B, C are in AP, then the middle number B is the arithmetic mean between A and C. Therefore, when A is the arithmetic mean between X and Y, then the numbers X, A, Y are in AP. We know that in an AP, the difference between the 2 consecutive terms is same. Therefore, T2 minus T1 is T3 minus T2. Therefore, A minus X is Y minus A. Therefore, 2A is X plus Y. Therefore, A is X plus Y upon 2. Thus, the arithmetic mean A between any 2 numbers X and Y is given by A is X plus Y upon 2. Let us solve an example by using the formula of arithmetic mean. If 25 is the arithmetic mean between X and 46, then find x. We know the formula a is x plus y upon 2. Here the arithmetic mean a is given as 25 and the second number y is given as 46. On substituting these values in the formula, we get 25 is x plus 46 upon 2. On simplification, we get x is 4. Therefore, the value of x is 4. When the two numbers are equal, that is x is y, what is the arithmetic mean between them? When x is y, then the arithmetic mean between them is a is x plus x upon 2, which is x. Let us now learn the geometric mean between the numbers. We have learned that when the numbers a, b, c are in AP, then the middle number b is the arithmetic mean between a and c. If three numbers a, b, c are in GP, then the middle number b is called the geometric mean between the numbers a and c. We will now find the geometric mean between any two numbers x and y. Let G be the geometric mean between any two numbers x and y. Then by definition of geometric mean, x, g, y are in GP. We know that in GP, the ratio between consecutive terms is constant. Therefore, T2 upon T1 is T3 upon T2. Therefore, g upon x is y upon g. On simplifying, we get g square is xy. Therefore, g is plus minus root of xy. Thus, the geometric mean g between any two numbers x and y is given by g is plus minus square root of xy. This means there are two values for geometric mean of any two numbers, that is plus square root of xy and minus square root of xy. Let us now solve an example by using the formula for geometric mean. Find the geometric mean of square root of 82 minus 1 and square root of 82 plus 1. What is the formula we have learned to find the geometric mean? G is plus minus square root of xy. What is the value of x and y given here? X is square root of 82 minus 1 and y is square root of 82 plus 1. Substituting these values in the formula, we get g is plus minus square root of 82 minus 1 into square root of 82 plus 1. By using the formula a minus b into a plus b is a square minus b square, and simplifying we get g is equal to plus or minus square root of 81, which is equal to plus or minus 9. Geometric mean of the given numbers is plus or minus 9. If the two numbers x and y are equal, that is, if x is y, then the geometric mean between them is g is plus or minus of square root of x into x, which is plus or minus x. Consider the following examples. If a is 5 and b is 8, then its geometric mean g is square root of 40, which is a real number. If a is minus 3 and b is minus 4, then its geometric mean g is square root of minus 3 into minus 4, which is square root of 12, which is also a real number. But when a is minus 6 and b is 7, then its geometric mean g is square root of minus 6 into 7, which is equal to square root of minus 42, which is not a real number. What do you understand from the above said examples? Geometric mean G will be a real number if and only if A and B have the same sign. Meaning of geometric mean. Geometric mean was proved by a well-known Greek mathematician Euclid with the help of a geometrical construction. We will now learn the geometric mean of A and B with the help of a geometrical construction. Consider a line segment AP of length A centimeter and a line segment PB of length B centimeter as shown in the figure. What is the length of segment AB? Since the point P lies between the points A and B, AP plus PB is AB. Therefore, the length of segment AB is A plus B centimeter. Draw a semicircle with AB as diameter. Draw perpendicular at the point P to the diameter AB. Let this perpendicular line meet the semicircle at C. Join AC and BC. We get triangle ACB inscribed in the semicircle. What is the measure of angle ACB? Angle ACB is inscribed in a semicircle. Therefore, measure of angle ACB is 90 degrees. Hence, triangle ACB is a right-angled triangle with right angle at C. Therefore, AB is its hypotenuse. In triangle ACB, angle C is 90 degrees. Segment CP is perpendicular to hypotenuse AB. Name the similar triangles in this figure. By the property of similarity in right-angled triangles, triangle APC is similar to triangle ACB. Triangle BPC is similar to triangle ACB. And triangle APC is similar to triangle CPB. We will consider the similar triangles triangle APC and triangle CPB. Therefore, AP upon CP is CP upon PB, since they are the corresponding sides of similar triangles. By cross-multiplying, we get CP square is AP into PB. Substituting AP is A and PB is B, we get CP square is AB. Therefore, CP is square root of AB. What is CP? CP is a perpendicular from the circumference to the diameter. Thus, the length of the perpendicular CP from the circumference to the diameter is exactly the geometric mean of segment AP and segment PB, that is, A and B. Let us now learn a theorem on the relationship between the arithmetic mean and the geometric mean of any two given numbers. The theorem can be stated as follows. Let x and y be any two unequal positive real numbers. If A is the arithmetic mean and G is the positive geometric mean between x and y, then A is greater than G. The proof is as follows. It is given that A is the arithmetic mean between x and y. Therefore, A is x plus y upon 2. It is also given that G is the positive geometric mean between x and y. Therefore, G is plus square root of xy. What is a minus g? A minus g is x plus y upon 2 minus square root of xy, which is equal to x plus y minus 2 into square root of xy upon 2. Using the formula a minus b the whole square is a square minus 2ab plus b square, we know that x plus y minus 2 into square root of xy is square root of x minus square root of y the whole square. Therefore, a minus g is equal to square root of x minus square root of y the whole square upon 2. Since x and y are positive, root x and root y are real. Therefore, root x minus root y is also a real number. The square of a real number is always greater than or equal to 0. Since x is not equal to y, root x minus root y is not equal to 0. Therefore, root x minus root y the whole square is greater than 0. Therefore, a minus g is greater than 0. Therefore, a is greater than g. We will now solve some examples based on arithmetic mean and geometric mean. Question 1. Sachin, Sehwag and Dhoni together scored 228 runs. Their individual scores are in GP. Sehwag and Dhoni together scored 12 runs more than Sachin. Find their individual scores. Let the number of runs scored by Sachin, Sehwag and Dhoni be x, y and z respectively. What is the total of the runs scored by Sachin, Sehwag and Dhoni? Sachin, Sehwag and Dhoni together have scored 228 runs. Therefore, x plus y plus z is 228. It is given that their individual scores are in GP. That is, x, y, z are in GP. Therefore, y is the geometric mean between x and z. Hence, y is square root of xz. Sehwag and Dhoni together scored 12 runs more than Sachin. Therefore, y plus z is x plus 12. Substituting y plus z is x plus 12 in x plus y plus z is 228, we get x plus 12 is 228. On simplifying, we get x is 108. Substituting x is 108 in y plus z is x plus 12, we get y plus z is 120. Therefore, y is 120 minus z. We have y is square root of xz. Therefore, y square is xz. Substituting y is 120 minus z and x is 108, we get 120 minus z the whole square is 108z. On simplifying, we get z minus 300 into z minus 48 is 0. Therefore, z is 300 or z is 48. Substituting z is 300 in y is 120 minus z, we get y is 120 minus 300. Therefore, y is minus 180. Since the number of runs cannot be negative, therefore, z is 300 cannot be accepted. Therefore, z is 48. Substituting z is 48 in y is 120 minus z, we get y is 120 minus 48, which is 72. Therefore, number of runs scored by Sachin, Sehwag and Dhoni are 108, 72 and 48 respectively. Let us solve one more question. If the arithmetic mean and the geometric mean of two numbers are in the ratio 5:4 and the sum of the two numbers is 30, then find these numbers. Let the two numbers be x and y. It is given that the sum of the two numbers is 30. Therefore, x plus y is 30. We know that a is x plus y upon 2. Substituting x plus y is 30, we get a is 15.